Hello students, welcome back to Algebra 2. We've got a little bit of an unusual lesson today. Today we're going to be creating exponential and logarithmic models based on given data. And the reason this lesson is so unusual is because since the writing of this textbook, technology has advanced, giving us more accurate ways and more efficient ways to solve these problems. So in this case, we are asked to find an exponential model that shows the relationship between the number of years a store has been in business and the number of trampolines that they sell. So if I were to look at this, this would be just going to draw a quick graph. If I had 1 was at 12, and then 2 was at 16, 3 is at 25, 4 is at 36, 5 is at 50, 6 is at 67, and 7 is at 96. I see that it is going to grow in an exponential manner. Now, if I look at this, I want to know how much it's growing by, because an exponential function is going to be multiplied by the same amount every time. So what do I multiply 12 by to get 16? Well, I can figure that out really quick by doing a calculation. 16 divided by 12 is equal to 1.333. Now, if it's a true exponential, that means that this pattern should follow. So if I do 25 divided by 16, I get 1.565. That's close, but it's not perfect. So let me do the same thing again. 36 divided by 25, 1.44, again close, but not perfect. 50 divided by 36, 1.38. 67 divided by 50, is 1.34, and then 96 divided by 67 is equal to 1.43. So all of these are pretty close, but they're not exact. So what I can do is I want to take one starting at the beginning and one at the end and kind of create an average exponential function of it. So what I can do here is I can take the basic exponential function is y equals a times b to the x power, and I can plug in 2 points. So let's just take the first one and the last one. So if I use the point 1, 12, that would be 12 is equal to a times b to the first power. Then if I take the last one, which is 796, I would get 96 is equal to a times b to the 7th. So now what I have here is a system of equations, and I can solve that by solving one of these for one of the variables. So let me take the orange equation right here, because it's just a times b, and let me divide both sides by b, so I would get a is equal to 12 divided by b. I'm going to take that value and substitute it in over here for a, so I would get 96 equals 12 over b times b to the 7th, and then I can solve that. Now, this b is going to cancel out one of these b's, so I would get 96 equals 12b to the 6th. We'll divide both sides by 12. 96 divided by 12 is 8, equals b to the 6th power. And then I will solve that by taking the 6th root of both sides. B is equal to, we'll use a calculator for this part, 8 to the 1/6 power 1.4142. Now that I have that, I can go back and solve for A. So, coming back over here, I have, let's use the simplest one, 12 equals A times B. But now 12 equals A times 1.4142. And then we'll just divide both sides by 1.4142. And then use our calculator for that. 12 divided by 1.4142 is equal to 8.4854. So my answer to this one is going to be, the equation is y is equal to 8.4854 times 1.4142 to the x power. Now, this one is a guess. So if I look at this, each of these has a different number that it got multiplied for. And so if I had chosen to use points 1 and 4 instead of 1 and 7, I would have gotten a completely different answer. And at this point, I don't really have a way of knowing that I picked the best one. So what I'm going to do now, this was the method that was taught 5-6 years ago, and it's valid, but it's a little bit flawed. I'm going to move over to my technology. So let's go over to Desmos, and what I'm going to do here is use a regression formula. So I'm going to add a table here and just say 1, 12, 2, 16, 3, 25, 4, 36, 5, 50, 6, 67, and 7, 96. I'm going to go ahead and maximize this. And let's adjust the scale so I can see it a little bit better. I'm going to go from 0 to 10 on the x-axis, and then we'll go from 0 to 100 on the y-axis. That way I can see all my points. So now I know we've done a little bit of regression in the past. The equation for an exponential function is y equals a times b to the x power. I'm going to make a slight adjustment to this because it's not going to hit every point perfectly. So instead of equals, it'll be approximately. And then looking at my table right here, I have x1 and y1. So I'm just going to change this to y1 equals a times b to the x1. And then I see that I've got a curve here that fits pretty nicely, but not exactly. So now I see that I've got my parameters. A is 8.9726 and b is 1.40265, which would give me the equation y is equal to 8.9726 times 1.40265 to the x power. Now comparing that to the work that I did by hand, my A that I got was 8.4854. This one was 8.9726. My B was 1.4142, where this is 1.40265. So they are close, but the difference here is that the one using Desmos is computer generated, and so it's gone through and using its algorithms, it's found the best one. So mine is okay, but this one is best. And also I feel like this one took a lot less effort on my part. So it's good to understand this method, but there's no reason not to use our technology in this case. So that being said, let's go on to another one. So the atmospheric pressure decreases with increasing altitude. So at sea level, the average air pressure is 1 atmosphere, or 1.033227 kilograms per square centimeter. The table shows the pressure in atmospheres at selected altitudes in kilometers. So use a graphing calculator to find a logarithmic model of the form h equals a plus b natural log p that represents the data. Estimate the altitude when the pressure is 0.75 atmospheres. So in this case, I'm going to go ahead and delete all of this. I'm going to start over, making a table. So in this case, instead of p, I'm going to make it x. So actually, yeah, h is the output, so that would be my y. So I'm going to say 1, 0, 0.555, 0.25, 10, 0.12, 15, 0.06, 20, and 0.02, 25. So let's adjust the graph a little bit. So basically all of my information is happening between 0 and 1. I'm going to make it 0 and 2. Maybe 0, 1.3. That way it spreads out. And on the y-axis, I'll make it 0 to 30. Okay, so I can see here that we started at 1 and then we went backwards and we're kind of approaching this vertical asymptote here. So it's like an exponential function, but kind of backwards. It's a logarithmic function, or in this case, a natural log function. Excuse me. So looking back at the text, it says, use a graphing calculator to find a logarithmic model of the form h equals a plus b natural log p. So I'm just going to put h is equal to a plus b ln p. That's my formula. Now I'm going to make a quick change because instead of h and p, I'm going to use x and y, putting them in the appropriate spots. And then again, it's not going to hit every point perfectly, so I'm going to use the approximate, and then I'm going to change this to x1 and y1. And there is my model right there. So I get r squared is 0.99. Remember, that's the correlation coefficient. That means it's a very good model. And my parameters are 0.862658 and negative 6.44738. So make sure that when available, you follow all of the rounding rules. But in my case, I would get h is equal to 0.862658 plus, or I guess minus, 6.44738 ln p. And this would be my model for that function.